Good morning, students. Today's lecture focuses on two closely related concepts: theories of homogenization and synchronization with HTST pasteurization. Homogenization reduces fat globule size, while HTST ensures microbial safety. Understanding their integration is essential for modern dairy processing lines. In this session, we will analyze breakup theories, two-stage concept, HTST basics, and system synchronization. Let us begin with the introduction to theories of homogenization. The central concept here is fat globule breakup. Three major forces are responsible: turbulence, eddy currents tear globules apart; cavitation, shock waves from collapsing vapor bubbles disrupt fat droplets; shear, velocity gradients and friction forces stretch and rupture globules. These three mechanisms operate simultaneously inside the homogenizing valve. Now let us understand the turbulence theory. The diagram shows a high-velocity jet zone. Large fat globules enter this zone. Intense turbulent eddies are formed. These eddies generate interfacial tension forces, stretching and rupturing globules. The critical zone is the high-velocity gap at the valve outlet and impact ring. Thus, turbulence is considered the primary force for droplet disruption. Next is cavitation theory. At the valve seat, a sudden pressure drop occurs. This forms vapor bubbles due to local low pressure. As pressure recovers, these bubbles implode violently. The implosion creates shock waves which shatter fat globules. Therefore, bubble collapse energy contributes to size reduction. Now we examine the shear theory. Milk flows through a very narrow gap, approximately 0.1 millimeters. Different layers of fluid move at different velocities. This creates velocity gradients. The resulting shear forces elongate fat globules beyond their elastic limit, causing rupture. Thus, frictional forces assist in breakup. This slide compares the three theories. Mechanism: turbulence, high-energy eddies tear globules apart; cavitation, shock waves from bubble implosion; shear, friction from velocity gradients. Together, they explain fat globule disruption. Let us now understand the two-stage homogenization concept. Stage 1, high pressure, typically around 15 to 20 MPa. This stage reduces size. Stage 2, lower back pressure around 3 MPa. This stage breaks clusters and prevents reagglomeration. Stage 1 reduces size, Stage 2 declusters. This ensures a stable emulsion and prevents cream plug formation. We now move to Introduction to HTST pasteurization. HTST stands for High Temperature Short Time. The standard parameters are 72 degrees Celsius minimum temperature for 15 seconds holding time. The system includes regeneration section, incoming cold milk is preheated by outgoing hot milk; holding tube maintains milk at target temperature; cooling section rapidly reduces temperature below 4 degrees Celsius. HTST ensures microbial destruction while preserving quality. Why must homogenization be synchronized with HTST? Process efficiency: fat must be in liquid state, required temperature range is 55 to 70 degrees Celsius. System balance: homogenizer is a positive displacement pump, flow must match HTST flow rate. Equipment safety: cavitation must be controlled to prevent valve damage. Therefore, temperature, pressure and flow must be synchronized. This slide illustrates integration of homogenizer with HTST system. The homogenizer is placed upstream of the final heater. This ensures any contamination from the homogenizer is pasteurized afterwards. Safety interlocks are provided. If HTST pump stops, the homogenizer also stops. PTF loop, pressure, temperature and flow are continuously monitored to maintain synchronization. Placement ensures safety and control. Here we see the complete dairy processing line. Balance tank, plate heat exchanger, regeneration, heater, two-stage homogenizer, final heater, holding tube of 72 degrees Celsius for 15 seconds, flow diversion valve, cooling section, filler. If temperature falls below 72 degrees Celsius, milk is diverted back for reprocessing. This ensures regulatory compliance. This visual summary consolidates the concepts. Breakup mechanism: turbulence is primary, cavitation assists, shear contributes. Two-stage process: stage 1 reduces size, stage 2 prevents clustering. HTST integration, placed upstream of final heater, requires 55 to 70 degrees Celsius inlet temperature. PTF loop ensures synchronization. The key themes are energy density, stabilization, safety. To conclude, homogenization theories explain how fat globules are disrupted through turbulence, cavitation, and shear. Two-stage homogenization ensures stability. Synchronization with HTST ensures microbial safety and process integrity. In modern dairy plants, homogenization and pasteurization must function as an integrated system. Thank you.